Let's be real for a second. If you think about it, the universe is basically a massive, impossibly complex video game. And today's explainer? Well, it's your masterclass on the ultimate game engine running the whole thing. We're tearing a classic textbook chapter on matter right down to its very atoms. We'll decode the underlying physics and use analogies that honestly are going to make these concepts stick in your brain forever. So, if you've ever found yourself wondering about the hidden rules governing literally everything you can touch, see, or even breathe, well, you're exactly where you need to be.
Here's the game plan. We're starting off with the cheat code to matter. Then, we'll map things out in the 3 states explained. After that, we hit heat, phases, and plateaus, followed by the power of pressure. And we'll wrap up the whole shebang with the unbreakable rule. Let's get right into it.
Section 1. Cheat code to matter. The kinetic molecular theory.
Okay, so this whole concept kicks off with one absolute fundamental truth. Matter is simply anything that has mass, the actual amount of stuff making up an object, and occupies space, meaning it has volume. Now, obviously, it's super easy to wrap your head around that when you're holding a heavy rock or a glass of water, but it applies to the invisible stuff too. The air you're breathing right this second, you can't see it, but it actually has mass, and it is physically taking up volume inside your lungs. It's all matter.
So to really get how this matter behaves, scientists rely on this brilliant sort of cheat code known as the kinetic molecular theory. Now, kinetic just means movement, right? And this theory breaks down into 5 key rules. Number 1, everything, and I mean everything, is composed of tiny particles called atoms, and when they link up, they form molecules. Number 2, there's always interparticle space, basically empty gaps between those particles. 3, we have cohesive force. This means particles naturally attract each other, pulling together like tiny invisible magnets. 4 is what I like to call the golden rule, rhythm. As the space between particles increases, that attractive force decreases. High space means low force, and low space means high force. And finally, number 5, because these particles are constantly jittering and moving around, they possess kinetic energy.
Let's really lean into that video game analogy for a second. Imagine these particles are players in an online match. Heat? Heat is literally a speed buff. The hotter the environment gets, the more kinetic energy those particles absorb and the faster they zoom around. This creates what scientists call Brownian motion. Basically, if you drop a tiny speck of pollen into water, the incredibly small water molecules will crash into that pollen from all sides, like crazy bumper cars. It causes the pollen to violently jitter around in this completely random, zigzag path.
All right, moving right along to Section 2. The 3 states explained, mapping the biomes. Let's zoom out from the microscopic world and talk about the macro states of matter we actually interact with every single day.
When we compare solids, liquids, and gases side by side, some really distinct rules emerge. Solids have a definite shape and a definite volume, because their attraction is extremely strong, so strong that the particles basically just vibrate in place. Liquids, on the other hand, ditch the definite shape. They still have a set volume, but with only moderate attraction, their particles can actually slide and roll past each other. And then, gases. Gases just throw the entire rulebook right out the window. Indefinite shape, indefinite volume, and near zero attraction. They're just doing some high-speed flying all over the place.
To really picture this, think of a solid like a massive wall built out of perfectly placed Minecraft blocks. Those blocks are rigidly locked into a 3D grid, and there's almost zero empty white space. They can't just spontaneously swap places. The cohesive forces holding them are so incredibly strong that they're stuck just vibrating right where they are, kind of like your phone buzzing on a desk. Now contrast that with a liquid. A liquid is way more like a crowded hallway between classes at a high school. You can't exactly break into a dead sprint, right? But you can shuffle, you can slide, and you can roll past the people around you to navigate the space. There are visible gaps. Plus, gravity pulls everyone down to the floor, which is why a liquid can fluidly take the exact shape of whatever container you pour it into.
And then we have gases. Gas is essentially a massive open-world battle arena. The particles are zooming around with extreme mobility and just massive amounts of empty space between them. The attractive forces here? Basically zero. Because they are completely detached from one another, gases have absolutely no definite shape and no definite volume. They will aggressively expand, bounce off the walls, and completely fill whatever container you happen to trap them inside.
Section 3. Heat, phases, and plateaus. Power-ups and hazards.
So how exactly do we travel between these different states? Temperature is the mechanism. It's the in-game power-up that alters kinetic energy and forces matter to shift states. When we add heat, we're adding pure energy. Step 1 is melting. You heat up a solid, and the particles vibrate so violently that they finally break free from their rigid grid, melting into a liquid. Step 2 is boiling. Keep blasting that liquid with heat, and the particles move so fast that they completely shatter those moderate attractive forces and escape right into the air as a gas. But Step 3 is where things get wild: sublimation. This is a highly specific case where certain solids, think of things like dry ice or mothballs, completely bypass the liquid phase. They just jump directly from a solid straight into a gas, no in-between.
And you know, the exact reverse is true when we take energy away by cooling things down. First up is condensation. This happens when a gas cools down, the particles lose speed, and those attractive forces finally have a chance to grab them back into a liquid state. It's exactly why you get water droplets forming on a freezing cold soda can in the summer. Keep cooling that liquid down, and you hit freezing, where the particles lock back into that super rigid Minecraft block grid. Now, what's the exact opposite of our wild sublimation phase? That's called deposition. This is when a gas bleeds off its energy so incredibly fast that it turns directly into a solid. The absolute perfect example of this is the beautiful, intricate frost that seems to form instantly on a window on a freezing winter morning.
Okay, before we go any further, we desperately need a quick, wait, really? Myth-busting moment. When you're boiling a pot of water on the stove, what is actually inside those big bubbles rising to the surface? Honestly, a lot of people just assume it's air that somehow got trapped in the water. But no, that is completely wrong. Those bubbles are literally water that has already turned into water vapor, a gas, down at the scorching hot bottom of the pot. And because gas is so much lighter than liquid, that little pocket of vapor rapidly shoots to the surface and pops.
Now this is really fascinating. Let's break down the master heating curve graph. If you picture the x-axis as time and the y-axis as temperature, the diagonal lines are straightforward enough. As time goes on, the temperature is rising, and only one specific state of matter exists during that period. But consider the plateaus. Notice those flat horizontal sections at the exact melting and boiling points? During a phase change, the temperature stays totally locked. It completely flatlines. Why? Well, because all of that intense heat energy you're blasting into the substance is no longer being used to raise the overall temperature. Instead, it's working overtime, literally doing the heavy lifting, to break apart the cohesive attractive forces between the particles. Until every single particle is completely freed, that temperature refuses to budge even a single degree.
Section 4. The power of pressure, crushing the players.
So we've seen exactly what temperature does, but believe it or not, temperature isn't the only tool in the universe's toolbox. Imagine a heavy glass cylinder packed full of orange gas particles, with a heavy plunger, a piston, sitting right on top. As that piston forcefully pushes down, it aggressively decreases the interparticle space. Remember our golden rule from earlier? Low space equals high force. By mechanically crushing these gas particles closer and closer together, you eventually make the empty space so incredibly small that the natural cohesive forces just take over. They grab onto the particles and forcefully change their physical state, and you didn't even have to touch a thermometer.
This very specific crushing mechanism brings us to the concept of liquefaction. It's the process of turning a gas into a liquid purely by applying extreme high pressure. And hey, this isn't just some abstract textbook theory, it's quite literally how we power huge parts of our everyday lives. Think about those LPG, liquefied petroleum gas cylinders that people use for cooking and heating. The fuel inside isn't natively a liquid, it's actually a gas that has been squeezed into a liquid state by immense pressure inside that heavy metal tank. The absolute second you open the valve on your stove, the pressure drops and it instantly flashes right back into a gas so you can light it and cook your dinner. Section 5. The unbreakable rule, the server's anti-cheat.
All right, we've spent this explainer exploring all the different rules of how matter moves, how it shifts, and how it changes states. But there is one final overriding concept. Think of this as the overarching boss-level rule of the physical universe. It's a server-level anti-cheat system that absolutely, under no circumstances, can be broken. Consider Hans Landau's famous H-tube experiment. He took an H-shaped glass tube, put sodium chloride in one leg and silver nitrate in the other. He sealed up the entire tube and weighed it perfectly. Let's just say for argument's sake, it was exactly 100 grams. He then tilted the tube, mixing the two chemicals together. A violent chemical reaction kicked off immediately, creating this thick, white, solid precipitate called silver chloride. It looked entirely different than what he started with. But when he took that sealed tube and put it back on the scale,
It still weighed exactly 100 grams. The atoms had simply rearranged themselves, almost like Lego pieces snapping apart and locking into a brand new shape. No magical new Lego pieces were added to the mix, and absolutely no pieces vanished into thin air.
So the crucial point here is captured perfectly in a quote by the legendary chemist Antoine Lavoisier. Matter can neither be created nor destroyed in a chemical reaction. This, my friends, is the law of conservation of mass. You can freeze it, you can boil it, you can crush it with extreme pressure, or you can violently chemically react it. But the universe? The universe always keeps perfect accounting. The total mass before any reaction will always exactly equal the total mass after.
As we wrap up this explainer, I want to leave you pondering a truly unique, kind of mind-blowing fact from the source material. It just proves how beautifully weird our universe really is. See, almost every substance in existence naturally shrinks and gets denser when it freezes into a solid. But water? Water is the universe's bizarre exception. As it freezes, its molecules actually expand outward into a rigid crystal ring shape. This is exactly why ice floats in your glass. So I have to ask you, what do you think would happen to the oceans if ice played by the normal rules and it actually sank? The terrifying reality is that our oceans would freeze from the bottom up, eventually turning Earth into a giant, lifeless ice cube, entirely wiping out all marine life. The fragile, miraculous, rule-breaking design of matter is literally the only reason we are even here to study it. Thank you so much for joining me today. Keep questioning the world around you, and I'll catch you in the next explainer.